Greetings, math fans. All right, so this is day 4 of our stats unit, and it's really just the second worksheet here, or note sheet. And so we're going to talk a little bit about distributions today, and some of the features of different distributions. So the first thing I want to talk about is we have something called a normal distribution, very significant distribution. Okay, normal distribution. So basically in stats, the normal distribution describes data that clusters around a meter average. All right, so you guys have probably seen the graph. Let's take a look at the graph actually. And it is a bell-shaped curve. Okay, it even says, if we go back here, normal distribution is a graph associated with a bell shape with a peak at the mean, and again is known as a bell curve. And you probably recognize this bell because you've probably eaten a Taco Bell, and that's what the bell looks like. Okay, so it's kind of where Taco Bell came up with this, is they are into stats. Never mind. Okay, so anyway, so this is your bell curve right here, and basically if I made a bunch of histograms, this is kind of what it's based off of. So if I made a bunch of histograms, which is just like your frequency, so histogram, and I made a bunch of histograms like this, right? I keep making it down like that, like that, like that. Again, the same thing on the other side. And I put all those histograms together, and I make them, you see a little gap here, but if I made them even tighter, you would get a nice bell-shaped curve like this, okay, on both sides. All right? So that is a normal distribution, which is a bell shape. So a couple things here, math fans. First of all, the word standard deviation, which you might have heard, the basic definition of standard deviation is how spread out the data is about the mean. Okay, so if the data is a lot more spread out, then there's a higher standard deviation. If it's less spread out, it is a lower standard deviation. Okay, and so basically, if I just kind of looking at some of these numbers here, this guy right here. Let's go back down here. Sorry. Okay, so this guy right here. So 68% of the data of a normal curve is one standard deviation or about the mean. Okay, so 34% to the right, 34% to the left. 95% of the data is within 2 standard deviations of that mean, and 3 standard deviations is 99.7% of the data is within the 3 standard deviations of the mean. Okay, so basically in industry here, math fans, many things are built within 3 standard deviations. By the way, which if you look just at the next thing here, it's called the empirical rule, which actually is important here. It states that for a normal distribution, so I'm going to highlight normal distribution because that actually is a really significant word which you will probably see many times. Empirical rule is for normal distributions, and basically it says that almost all values lie within 3 standard deviations of the mean. Okay, and that's important. So empirical rule is used a lot in industry. For example, the height of a door frame is about 6'8". Well, that's within 3 standard deviations of a person's height. So if the average person's height is about 5'10", the average male is 5'10", 3 standard deviations away is about 6'8". They're trying to develop most things to fit most people. Okay, Yao Ming is like 7'7". They don't build cars, they don't build doorways, they don't build a lot of things to handle a guy the size of Yao Ming because there aren't many people that are 7'7". And here's the deal: if you try to build something that handles everybody, you're actually wasting a lot of money, right? If I would build all door frames that handle somebody who's 7'7", that means I'm actually spending more money on doors, on the frame, even on the height of the ceiling, the size of a car. It just, they don't, if you build a car that holds a 7'7" person can drive the car, how many people are going to come into the showroom that are going to be 7'7" that are actually going to buy it? What, 3 maybe a year? Probably such a few amount, maybe nobody, because Yao Ming is not going to come to your dealership. Okay, so you can't build it for everybody, but you got to build it for most of the population. That's why we use the empirical rule, because it does build it for most of the population. In fact, it builds it for 99.7% of the population. That's most of the population. 0.3% is not going to work. It's not going to build it for really short people, and it's not going to build it for the really tall people. Okay, so very important. The empirical rule for standard deviation. again, 3 standard deviations. Okay, so something we use a lot in standard deviation is something called Z-score. And basically, if I say a standard deviation, let's say if I compare my height, I'm about 6'2.5", 6'3", and if I said, well, I'm within 2 standard deviations of the average height of a male of 5'10", but you didn't know anything about me, you would go, well, Mr. Griffiths, so are you taller than the average male or shorter than the average male? Because you just told me I'm 2 standard deviations away, and I'd be like, good point. That doesn't describe everything. It just tells you how far you are away from me. It doesn't say higher or lower. Well, what the Z-score does, it actually tells you if you're higher or lower or above the mean or below the mean. Okay, so standard deviation can be basically can be positive or it can be negative, and that's to show direction from the mean. Okay, and again, standard deviation is basically only positive. So if you have a Z-score, let me erase this here. If you have a Z-score of -2, that means you're 2 standard deviations below the mean. A Z-score of +4 means you're 4 standard deviations above the mean. Very simple. Okay. The next thing I want to talk about is something called variance. And variance is actually a pretty simple thing. It's simply the standard deviation squared. Okay, you square the standard deviation. Basically, it's used a little bit in statistics. You need to know it. But one advantage of squaring standard deviation is that it adds more weight to the larger differences. When one of the standard deviations might be, let's say 4 inches. Okay, as if you have 2 standard deviations at 8, it's 8 inches. If you square that, it's 64. So it makes the bigger numbers more significant. Okay, that's kind of one of the uses of variance. But the deal is, and you should know that, it's the standard deviation squared. That's actually pretty key. Okay, so let's just kind of talk a little bit about it. When is the standard deviation going to be equal? When is the standard deviation equal to the variance? So let's write that out. When is the standard deviation equal to the variance? Well, when the standard deviation is 1, because 1 squared is 1, or 0. 0 equals 0, right? If the standard deviation is 0, what that means is everybody's the same. So if I literally in the classroom, everyone was 6'2.5", the same size as me, and I said, hey, what's our distribution look like? This is what it would look like. Ready? Watch, I'm going to draw it. Ready? It's a line, a vertical line. Because there's no movement on either side. There's no standard deviation. It's just one line. It's like one single bar for a histogram. Okay, but of course, it's a bell-shaped curve because people aren't 6'2.5". They're taller and shorter, and that's why it gives you your bell curve. Okay, so anyways, this is where it's equal. In this case here, where would the standard deviation be greater than the variance? Well, remember, the variance is the standard deviation squared. So if the standard deviation was the standard deviation is 1/2. Do you guys agree with that? Because I'm looking for where standard deviation is greater. If it's 1/2, what happens when you square it? You get 1/4. So there you go. When basically this guy is a fraction, so it's between 0 and 1. Okay, so I can actually use parentheses between 0 and 1, not including 0, not including 1, it would be greater. And the standard deviation is less than the variance, because when you square the standard deviation, if it's, let's say 2, if I square it, 2 is less than 4, right? So that would be basically anything greater. So we're going to say a bracket. Actually, it's going to be a parenthesis because not equal. So from 1 to infinity. That's where it's going to be greater. Okay, because you get 2 squared, 3 squared, 4 squared, you square it, and it's bigger. Okay, so that's kind of important. I would definitely know this, and I would know this guy right here, and I would know this guy right here. Okay, that's pretty important. All right. Okay, so let's keep going here. All right, so let's talk about bimodal distributions. Basically, we talk about bi means 2, and mode means something that occurs twice. right? If it's trimodal, it occurs 3 times, right? And that's the most that something occurs. It happens that 3 things occur the same 3 times, right? So these these are distributions, and we really haven't talked about distributions. So this is a distribution here. And basically a distribution, just if you kind of just scan this, here's one mode right here, and here's another mode right here. So that one makes this one bimodal. Same thing with this, with the curves. 1 mode and 2 mode, something occurs twice. That 0.2 occurs twice. Okay? So again, you don't have to have the exact number here for these histograms, but as long as you see a certain area is repeated twice, that would be bimodal. Okay? A good example of something bimodal is if I gave you a really tough test and some people studied and some people didn't. So some people got an A because they studied, and some people didn't study and they earned Fs. So there weren't a lot of Ds, Cs, or Bs, so that's what makes something bimodal. Okay? The next thing we're going to talk about is something called trimmed mean. And trimmed mean is averaging method which eliminates a partial percentage of the greatest and smallest values before finding the standard mean of a given data. So basically, here's the deal. If you've got, I've got a bunch of kids in my class, and I want to find out, hey, what's the mean of our class? But I want to do a trim mean of about, 10%. I want to eliminate the people who are like 6'10" because they're going to really mess up the mean. And we've got, some little first grader is a super genius, and he's like, 3'5". I want to eliminate his height too because he's going to kind of mess up my average. I want to get a good average of the people in my classroom. All right, so let's look at this example. Given the data in numerical order 1, 3, 3, 7, 8, 9 right here. The question is find the 20% trim mean. Okay, so 20% is 20 divided by 100, which is 0.2, and my sample size is 0.6. That's how many pieces of data I have, or 6. So my trim mean count is basically this guy right here. It's 6, the sample size, times the 0.2, which is 1.2, and I round that to 1. So what I'm going to do is I'm going to take that 1, I'm going to remove 1 piece of data from the lowest and highest of the data, and then I'm going to calculate the mean like I do already. So I'm going to eliminate this 1 here, and I'm going to eliminate the 9 here, and I literally just have 3, 3, 7, and 8 left over. And so I find the mean of that guy, 3 plus 3 plus 7 plus 8 divided by 4, and my trim mean, trimmed 20% mean, 20% trim mean is 5.25. Okay? It's pretty easy. All right. Let's talk about skewed data. You might hear some people talk about if the data is skewed because you had a brainiac and they studied really hard, they kind of skewed the data, or maybe you had a bunch of people who cheated and they skewed the data, or you had some people who didn't even study for that, so they kind of skewed the data too. So skewing the data is basically some unusual person maybe studying more or studying less, and changing the data. So if you have a negative skew, so let's look at the first one here. If you have a negative skew, the left tail is longer. So this is a negative skew down here. And you can see the left tail over here on the left. This is longer. And it's long, basically, but the mass of the concentration is still here. It's still to the right of the graph. Okay? And it has very few low values. So it has few low values and more higher values. For a positive skew, here's a positive skew, is the right tail is longer. Here's the tail, and it's longer. And the mass of that distribution is concentrated here on the left. Okay? It has very few high values, so very few of these high values, and more low values. And so we say that's skewed to the right. Now here's a good way to remember this. Okay, let me just show you. If it's skewed to the left, look at like it looks like an arrow, doesn't it? It looks like an arrow pointing this way. So if it's pointing this way, that means it's a negative. It's pointing to the negative side, right? And if the arrow's this is here, a skew is kind of pointing to the right, then we say it's a positive skew. Okay? So you got a negative skew and a positive skew, which way that arrow points. It's kind of easy to remember that. So let's ask a couple questions here. What is better for the average of a skewed distribution, mean or median? Okay. Well, here's the deal. Let me erase this ink here again. If I'm looking at the graph, what's going on is median still cuts the data in half as far as high and low. It doesn't matter if the low point is really, really low or kind of low, it still cuts the data in half. Still cuts in half. Okay? Maybe that's not a great half. Maybe a little bit more over here. I don't know, but that's okay, whatever. Okay, so it cuts in half. So it doesn't really care about this. It doesn't care about that. So that's actually the better estimate for to using median to figure out the average as opposed to mean, because these values here and these values here, they actually stretch it out. So the mean is actually going to be pulled more this way and more this way, and it's actually going to make it a little more inaccurate because of these brainiacs studying for the test, or the people cheating, or you have few people that had no idea what they're doing, pulling it to one side or the other. Okay, so definitely the answer to this one, the better average is mean or median. Okay, all right, and then the next part is, would you rather have a positive or negative skew for the test? Well, again, if you look at the graphs here, what would you rather have? Well, I think I would rather have a negative skew. And the reason is because, as you see in negative skew here, it says the mass of the distribution is concentrated on the right, which means most people got good grades, and you only had a few slackers that didn't study. Okay, so I would definitely rather have a negative skew because more people are going to get good grades. Okay, not bad. All right, so let's do a Z-score problem here. Your final exam grade is an 80%, and the mean of the final exam is 90%. The standard deviation of the final exam is 4. What is your Z-score for the final exam? Now, don't you guys agree that you've actually scored worse than the final exam, the mean of the final exam? So you guys should know your final exam, the Z-score, is going to be negative because you're scoring below the average. And so if the standard deviation is 4, so for every 4 you go down, that's 1 standard deviation. So basically this is what you're going to do. You're going to say you're 80% minus 90%. So what you got, so this is you minus the class. Okay, and that's going to be negative 10. And you know it's negative. If you do it the other way and say 90 minus 80, that's okay, but you got to make sure you make it negative because you're below the average. So the Z-score is negative. And there are 4 standard deviation, or for every standard deviation is 4%. So I'm going to divide this by 4, and so my standard deviation is negative 2.5. So you're 2.5 standard deviations below the average of this test. Okay, because you multiply 4 times 2.5, you get 10. 10 plus 80 is 90. Okay, so this is your Z-score. Okay, pretty easy. All right, so let's do a problem with your graphing calculator here because I want to show you how you can use your graphing calculator. So let us shrink this a little bit here and bring up the graphing calculator. All right, so I'm going to kind of, just so you can see it a little bit easier there. And what I'm going to do is I'm going to hit the stat key, because all the directions are here on that page, but let's just do it. So I'm going to hit the stat key, and I'm going to do setup editor because I always like to hit setup editor, which is kind of nice. Okay, it kind of resets the column. And then I'm going to hit stat, and then I'm going to hit edit. And I'm going to enter my data. Now this is data from last worksheet, so I'm just going to go to the top of this. Don't hit delete. Remember, if you hit delete, you'll actually delete the whole column, and then you got to hit setup editor to bring it back. But I'm going to hit clear. That's the best. At the top of the column, and that clears all my data. Okay, that's pretty sweet. So literally the data that I'm asking you guys to enter, if you're looking at your sheet, you're going to enter 1, 2, and 3. Right, 1, 2, and 3. Okay, and then what you're going to do is you're going to hit your stat button again, and you're going to do calculate, cursor over to calculate, 1 variable stat, and you're going to enter. And it's kind of cool. So that X bar means your mean, so that's 2. The sum is adding all those numbers together, so 1 plus 2 plus 3 is 6. the sum of all the terms squared, 1 squared plus 2 squared plus 3 squared is 14. Again, that's not something that you necessarily need to know. Okay, and then this S, we're not going to really worry about that. But see this little, it's like it's a small sigma. Okay, this little sigma here, sigma x, that's 0.816. That is our standard deviation. And by the way, that n right there is the number of terms. In fact, they give you the 5-number summary. Oh, look at that. Q3 and max, and that's how you get it, okay? So that's kind of cool. So you can cursor back up again. But we're concerned about the standard deviation. So our standard deviation is 0.816. All right? And like I said, and the average of this one was 2. So that's kind of good. Okay, so that's how big of a standard deviation? That's actually a pretty low standard deviation, 0.816. But of course, I only typed in 3 numbers. So it varies. So it's 0.816 is actually kind of significant compared to that, but it's what it is. So let's type in numbers that are spread out even more. So let's go back to stat and edit. And let's put in 3, and then let's do 4, 5, 6, 7, 8, 9, and 10. Okay? And let's do the same thing. Let's hit stat, cursor over to calculate, one variable stat. So we're going to go from that 8.816, and our standard deviation now is 2.87. Okay? So that's what happened. It's more spread out. The data is more spread out. It's more of a bell curve, right? As opposed to the other one, it's like a really tight bell curve. And that's why the standard deviation is higher, because it is more spread out. Okay, that's pretty easy, right? It's kind of mellow. All right, let's go back to our Word document here, or our document, and so we did, like I said, we just covered this stuff right here. So last thing here is just kind of looking at a real life use of a standard deviation. So let me bring this down here just so we have everything in line. Okay. I got this from a website here. I have the website posted up above here. It says people come in a lot of different heights. I just like height because it really shows the bell curve. I like a lot. Okay, so let's think of the height of American men. The average height is 5'10". This means half of all American men are taller than 5'10", and half are shorter. This one fact does not tell us much about how the height is distributed, however. One could ask, what's the tallest American man and the shortest? How many men are over 6'6"? Suppose you measure the height of 100 men chosen at random. Would you most likely measure something much like the following table? Okay, so here it is. This is kind of the curve here. And again, out of 100 people, you can see between 5'9" and 5'10", you're going to get about 17. So the average is right between 5'9" and 5'10". And, and then you have the different heights. One person would probably be about 6'4". 3 people would be 6'3". 4 people at 6'2". One guy might be 5'3". 3 or 5'4", 4 or 5'5". So you can see it's a small number out of 100, but most of those people are going to be, right here in the 5'9" to 5'10" area. Okay, so let me erase this here. Just kind of reading here. I don't want to read everything, but it said it turns out that this is a standard distribution, okay, a Gaussian curve or a bell curve. Okay, out of 100 men, 2/3 of them, about 68%, are between 5'7" and 6 feet tall. Okay, and about 2/3 of all American men are 5'10" plus or minus 3 inches. 1/3 of them are outside the range, with half of them are on either side. So 1/6 of them are 6'1" and taller, and 1/6 or 5'6" or shorter. So this is kind of like how the standard deviation works here. Okay, so you start getting, if it's 2/3 of all are plus or minus 3 inches, that's one standard deviation. So somebody about between 5'7" and 6 feet tall, that's going to be one standard deviation. All right, and then you go 2 standard deviations. That's going to be someone past like 6 6'1", 6'2", and anyway, I kind of listed a few of them here. If you were out 3 standard deviations, so some people, you guys probably recognize Michael Jordan. Okay, so here's some interesting 3 standard deviations and 4 standard deviations and 5 and 6. Okay, so Kobe Bryant, 6'7", Larry Bird, Karl Malone, these are old basketball players, 6'9", Shaquille O'Neal, Will Chamberlain, Kareem Abdul-Jabbar, 7'1", 7'2", and there's Yao Ming. He's, I guess, 7'5". So if I look at the U.S. population this tall, people who are 6'6" and 6'7", there are a lot of people. There's 2.1 million people that are 6'6" and 6'7", and you're like, whoa, that's a lot. Yeah, but that's out of the population of how many people we have in the United States? What, 800 million or whatever? So it's, pretty small amount. And then, of course, when you jump up to 6'9", all of a sudden that shrinks almost 10% of that is 135 then. And then you go even one notch higher, 7'1", 3,200. That's not a lot out of 800 million people. And then, of course, 7'5". I don't even know if there anybody. Is there anybody that's 7'5"? Maybe there's some people, but not many. 5 people. All right. So again, this is kind of going to showing you the standard deviation here, as opposed to looking at the graph, right? So if you're between 5'7" and 6'1", you're basically kind of average. And then you go one notch down, that's going to be 1 standard deviation. So I know I'm 1 standard deviation. I'm about 6'2.5", so I'm 1 standard deviation away from the mean. This is, again, the number of people in the United States out of 100 million people. I think there are more than 100 million people, but that's what it shows. Okay, and then 2 standard deviations, you're down to 5'1" to 5'4", and 6'4" to 6'7". So again, that's being pretty tall, and that's when now we start getting to super short and super tall people, and even shorter, 4'7". Not a lot of people with 4'7", right? That's pretty low, and again, that's pretty high, and then we keep working our way up, and we get really high. Okay, so in industry, things are made for 3 standard deviations. So a lot of things are made to handle this. Not so much this, though. I'm going to tell you right here. Not so much the 3rd standard deviation, and even not so much this. It starts to, like when you buy a car, you're not even handling this. It certainly can handle this, because cars can handle short people, because you just move the seat up. Right, and you have people who have more leg room in the back, but you can only crunch people in the back so much, and that's why you don't really have these people who are 6'5", 6'6", 6'7" that can easily fit in the front of a car. You have to get a bigger car or get your seat moved back, and then when you start getting crazy like this, well, they're not going to build a car that holds just for 3,200 people or 28 people or 5 people. That's ridiculous, right? They're just not going to build a car like that. So anyway, that's just kind of, we spent a little bit of time just kind of talking about distribution. I think it's kind of interesting, talking about the normal distribution and how it's used in industry. But hopefully you guys learned a little bit from this. And this is our last unit for M408. So hopefully you guys had a good year, and stay out of trouble, and good luck in calculus. And don't forget to save for retirement. That's what I always talk about in here. Okay? Talk to you later, math fans. Adios. Goodbye.